Hello, AP Chem. So anyways, I should probably start off with a few things. Firstly, your AP test is not going to be the normal AP test. Right now, it's going to be a 45-minute take-home test. And it's free response, all free response, no multiple choice. So a lot of your work is just going to have to be, working through problems and stuff. It technically only goes through chapters 1 through 7. So I have a meeting tomorrow with the science department, and I'll find out then kind of what I should do, because we're in the middle of Unit 8. Well, kind of in the beginning of Unit 8. So technically we're kind of done with what you need to know. But I want to keep going, because literally after we finish the AP, I'm still going to show you this stuff, because if you plan on taking any more chemistry in college or whatever, you're going to need to know this. And I don't want you to be behind the curve when you step into college and you don't have more acids and bases and thermodynamics. We should probably look at a little bit of electrochem before the actual test. And I don't even know when the test is given. Apparently April 3rd, we're supposed to find out some more information. So, okay. So that's what I know. It's 45-minute, take it home, free response, I believe. And it's only up to the end of equilibrium. So what you're going to see today, and, or if you're doing the Sunday night's work, is it might not be actually on the test, but you should know a little bit about these things. So, and then, like I said, after we'll actually go through it. So let me prop you up here and get you going. So today we're going to learn a little bit about percent dissociation, and percent dissociation, and I'm gonna show you the pH of bases. Hopefully you like this, because I just ordered these expo markers. They just came through on Amazon. So first thing, percent dissociation is actually like a pretty easy concept, and I mentioned it yesterday when I was doing this, or Friday, but I was doing this. But usually what you have is you have some like some HX, like some weak acid or whatever. If it was a strong acid like HCl, then the percent dissociation would be like close to 100%, like 99.99%. But if it's a weak acid, your percent dissociation is going to be pretty low. Usually around somewhere probably less than 5%. Some weak acids go as high as 50%, but the percent dissociation is going to be fairly low. So we take some weak acid, so I'll call it HX, and actually I'm going to do number 78 on page 598. B. Number 78 is like a good example of where you're going to see percent dissociation. So it says a 1.0 times 10 to the negative 2 molar HOCN, cyanic acid, is 17% dissociated. And it says find the Ka. Okay, so I've really been kind of harping on this all along. You have to make the formula with these acids. So what you would do is you'd say, all right, well, I got HOCN plus water, and it forms H3O plus OCN minus. That you should be able to do. And again, we're going to set up our ice table. So we got a 1 times 10 to the negative 2. So that's just 0.010 HOCN. And 0, 0. Then it says it's 17% dissociated. So percent dissociation is basically this number. So when we go like minus x plus x plus x, and then 0.010 minus x, x, and x, and I'm saying, I'm looking for my percent dissociation. The percent dissociation is this number, this x. So it's that x over 0.010 times 100 equals that, your percent dissociation. So if it's kind of weird. Sometimes they have you solve for the, they give you the Ka and have you solve percent dissociation. This one gives you the percent dissociation, has you solve for the Ka. So in this case, what you do is you'd say, all right, well, I know my percent dissociation is 17, so you'd go x over 0.010 times 100 equals 17. You'd solve for x, which should be 0.0017, I think, but let's just check it out. Oh, whoops. Yeah. So x is 0.0017. And then now that we know our percent dissociation number, now we know our x, we can then plug that in here. And so this becomes 0.0083, 0.0017, 0.0017. And now our Ka, I'll just put it up here, is H3O plus times OCN minus over HOCN. And if I plug in these values, 0.0017 squared over 0.0083. I should really check that. I just did that in my head. Yeah. Okay, so then I got that. And I'm getting 3.48 times 10 to the negative fourth. You see here? Yeah. 3.48 times 10 to the negative fourth. So there's your Ka. All right. So that's like a pretty easy question. It's actually not that bad. Let's do one in which they give you the Ka and you solve for the percent dissociation. So I actually ordered an eraser too. Okay. Let's do okay. We'll do 75 A. So this is a 0.50 molar solution of acetic acid. You know how I keep saying like acetic acid is just going to keep coming up. So acetic acid has a Ka of 1.8 times 10 to the negative fifth. Okay. Am I going to run into trouble there? Let me just make sure. Because if I am, I'm going to get my other calculator. I think I'm okay. No, I'm good. Okay, so what we got is we have our acetic acid plus water gives us H3O plus AQ plus C2H3O2 minus. And I'm going to start off with 0.50. Going to go through my ice table. I don't need that. And then 0, 0, minus x plus x plus x, x, and 0.50 minus x. X squared. Oh, sorry. So let me just do Ka is H3O plus times C2H3O2 minus divided by HC2H3O2. Good. It's funny. Natalie, you can actually see this now. That's pretty good, right? I'm actually giving you a lot of space so you can actually see here. So then it's going to be x squared over 0.50 minus x equals 1.8 times 10 to the negative fifth. And now, you remember yesterday I was saying, like, if you have a pretty low Ka, you can make this this approximation and just make it 0.5. For most of the times, you can just go x squared over 0.50 equals 1.8 times 10 to the negative fifth. X squared equals 9 times 10 to the negative sixth square root. And you get x equals 0.0030. Okay. So now if I'm asking for the percent dissociation, I am just going to go, all right, it's going to be the x, right? It's this over that times 100. 0.0030 divided by 0.50 times 100. And I end up with 0.6%. If I was asking for pH, even though it's not, always good to practice this. Negative log of H3O. So negative log of 0.003. And that gets you 2.52. You don't really need this. This is just for, whatever. This is the actual question here. All right, so there's a couple practice ones. I think I'll put on a question that you have to go in reverse, and I'll let you work that one out. That's probably a pretty good homework question to do. I also wanted to put up a little base stuff because that's the next thing that you're gonna see, and I'm gonna do a little callback to what I was talking about before, because bases. Remember, sometimes you get the OH and sometimes you don't. So you really want to make sure that you know how to do those weak base formulas, the weak base solutions. So let's first start off with mentioning that we do have a Ka expression. Sorry. Do I want to go through this? Let's just do... I know I mentioned the Kb, the base dissociation constant, and the most important thing for you to remember is weak bases usually don't have OHs, and so you need to react them with water to get an OH. So, for instance, like, I guess, question 86A says, aniline, write the reaction on the corresponding Kb expression, and aniline is C6H5NH2. And so remember, what you're going to do is you're going to react it with water. If it doesn't have an OH, you must react it with water and treat this as a Bronsted-Lowry base, which means the H pluses are going to kind of like hook over to there, and then you're going to get a nice C6H5NH3 plus, and this is the most important thing, that little OH business. Now that OH is super important because now once you solve for it, you can find your POH, and then you can find your pH. So, all right. So if I told you, and I don't know the KB of this, I'll find it. I wonder if there's a better question here. Oh, yeah. Okay. Okay. So as long as you're okay with this, it's gonna follow the same path as the acids are. So you're gonna start like ice table, blah blah blah, 0 0 minus x plus x plus x. Same business, except this time you're gonna have to deal with the KB. So your KB is going to be C6H5NH3 plus times OH minus all over C6H5NH2. Once again, don't put the water. Okay, so now we're going to take a look at a nice simple question number 96, which says we want to see hydrazine. What's going to happen with hydrazine? So it tells us that hydrazine, and if you look at the equation, I'm not going to write it all out here, but it basically is, this is what it's telling us. N2H5 plus OH minus. So it's giving you the KB reaction, but you should know how to do that. You should know how to do that. So it's N2H4, sorry. N2H4 plus water gives you those two things. And then it says the KB of this reaction is 3 times 10 to the negative 6th. Now, really important thing. There is a relationship between Ka and Kb of acids and their conjugate bases. So if I said, I want to know something, I actually do know something about N2H5. This is the conjugate acid of N2H4. And the way this works is kind of like, it's very similar to H plus and OH minus. You know how H3O plus and OH minus, if you multiplied those together at 25 degrees, you'd end up getting 1 times 10 to the negative 14th. Well, it turns out that the Ka times the Kb, as long as they're conjugates, will also equal 1 times 10 to the negative 14th. And I could actually go through and show you it's basically just a little bit of kind of like Hess's law. Remember with the Ks, you could combine two reactions. It turns out that the K and the Kb, if you multiply them together, as long as they're conjugates with each other, you'll get 1 times 10 to the negative 14th. So if I said, hey, I want to know what the Ka of this thing is, all I would do is go, all right, well, x times 3 times 10 to the negative 6th equals 1 times 10 to the negative 14th, and I could solve for it like that. 3.33 times 10 to the negative 9th. But that's a very weak acid. The lower your Ka value is, the weaker the acid. Lower Ka, weaker acid. The lower Kb, the weaker the base. But interestingly, and before I get into this question here, I just want to show you an extra thing here. If I have two acids, so let me just use that last one. So 3.33 times 10 to the negative 9th is my Ka of N2H5 plus, and then I said HF, the Ka is 6.8 times 10 to the negative 4th. I'm pretty sure that's right. So if I was looking at these two acids and said which one's stronger, well, that one is, because Ka 6.8 times 10 to the negative 4th is a higher number than 0.000000000 3, 4, 5, 6, 7, 8, 3, 3, 3. So this is a stronger acid, but the relationship between that and the conjugate base is F minus versus N2H4. These are the conjugate bases. So the stronger the weak acid, the weaker the conjugate base. So this is actually a weaker conjugate base than this one. You could calculate it pretty easily, like just do this times x equals 1 times 10 to the negative 14th, and this times x equals 1 times 10 to the negative 14th. You could find your KBs, but I'm just telling you, if you have a stronger weak acid, like this is stronger than that, then this is a weaker, the conjugate base is a weaker base than that. So that's like just a relationship. Okay, here we go. Exciting. So we go, I think they tell us they have a pH, they want the concentrations and the pH of a 2 molar solution. So we're going to do extra here. We're going to say, all right, I've got this 2 molar solution, 0, 0, minus x plus x plus x, 2 minus x. So my Kb expression is N2H5 plus times OH minus all over N2H4. So I plug in these values, x squared over 2 minus x equals my Kb, which is 3 times 10 to the negative 6th. And I can do that same exact thing with small kb. Easily done. I can just make this 2. So it would be x squared equals x squared over 2 equals 3 times 10 to the negative 6th. X squared equals 6 times 10 to the negative 6th square root. X equals point. Can you see this? Yeah. Okay. 0.002449, etc. I probably have 2 sig figs there. Now, what you're going to do is this happens to be the concentration of OH. And so, if I go negative log of OH, I get my POH. So, negative log of that answer will give me 2.61, and then my pH plus POH equals 14. So now my pH is 11.39. Okay, so what it was asking for was the pH. It was asking for these concentrations. So this is 0.00. Let's make it 24. 0.0024. And then 2 minus, that's basically 2, but 2 minus 0.002449. It's basically 2. So this is also going to be about 2. It's not changing all that much. That x is really small. And then the last thing I just want to show you is the percent dissociation, and then we're done. So the percent dissociation is just this over that times 100. So I'm just going to erase this. And my percent dissociation is 0.002449 divided by 2 times 100. And 0.12%. Even though they weren't asking for that, like, we'll just throw it in there as an extra question. Okay, so once again, it's I put a video up of Ruby if you want to see Ruby flying around. She doesn't like to let go of a frisbee, and where it's kind of keep going here. We're pretty close to the end of this section. I guess we have acid-base properties of salts. That's actually pretty easy. And structure and strength of acids and bases. So, a couple more days of stuff, and then we'll be finished. So, it's again, miss y'all, and hope to see you soon. All right, bye bye.